A lot of transportation problems are maximization, minimization problems. However, in some case situations you may find that it's articulated as a maximization problem. So here's an example of a maximization problem where we're trying to maximize profit with minimizing shipping costs being part of the profit equation, because minimizing costs is part of increasing profit. So here's the situation. You've got Acme Corporation, has two plants. Plant 1 can produce up to 44 million pounds of zinc, and Plant 2 can produce up to 28 million pounds of zinc. At Plant 1 it costs $21 to refine a pound of zinc, and at Plant 2 it costs $19 per pound. Acme sells to two countries, South Korea and France, and the shipping costs per pound are shown below in this table here. So Plant 1 costs $240 per pound, $2.40 per pound to ship to South Korea. It costs $2.65 per pound to ship to France, etc. So South Korea is willing to buy up to 28 million pounds of zinc at $60 per pound, and France is willing to buy up to 48 million pounds of zinc at $62 per pound. So how many million pounds of zinc should each plant ship to each country to maximize profit? And this is where we go into a maximization rather than a minimization minimization problem. And what is the maximized profit is the other question. So one way you can get these problems conceptualized is by using this type of a network diagram, where you've got the plants, which are the origins right here, and you've got the destinations, which are South Korea and France. Over here we have the capacity of each plant, 44 million and 28 million for Plant 2. Cost per pound at $21 per pound and $19 per pound at Plant 1 and Plant 2. The shipping costs are along the arcs from each origin or each plant to each destination or country. And then we have the actual costs associated with each shipping route per pound of zinc. And then we have the demand for each destination listed over here. And these problems are laid out in this format every single time you see this type of transportation problem. Now, what we have to do is we have to lay out all the inputs in this case. So for example, Plant 1 and Plant 2 has these costs, $21.19, taken straight from the problem over here. The cost per pound of shipping is again taken from the table that was given in the problem statement to the right. And the selling price per pound was taken from the problem as well, at $60 per pound at South Korea and $62 per pound from France. Then in here we have the decision variables, which is laid out just like the shipping area right here, where we have the plant and the destination countries, except this time we have to add the sum that comes out of Plant 1, so that's the sum of this row, and Plant 2 is, this is a formula right here in cell D19, which is the sum of row 2, and that the capacities taken from the problem are listed to the right. The sum that comes out of each plant must be less than or equal to its capacity. And then we have this column, which is the sum of this column must be less than or equal to the maximum demand, and the sum of this column, which is given right here, must be less than or equal to the maximum demand for France. All those values in blue here are taken from the problem that we just did. So in order to figure out the profit, we need to first of all come up with what the refining cost is of the solution. So to do that, what we have to do is we have to take the sum product of B5 and B6, which is these two, multiplied by and added to the sum of the product of these two. So that's where this formula comes from, right there. Sum product B5 to B6, D18 to D19, which is here. So these two and these two. And then the shipping cost is taken by doing a sum product on all this, multiplied and summed of all this. And that's what this formula does. And then the revenue is going to be the sum product of these revenue figures multiplied by the sum product of these total figures. The profit is just going to be equal to, and the sum is the B27 minus the sum of these two values. Okay, so that gives you the layout of the problem. So to solve this in Solver, what you need to do is you need to go to Data, Solver, And then you want to set your objective, which is the profit figure we just indicated, to a maximum, not a minimum like a lot of other transportation problems, but a maximum, by changing the decision variable cells, which are these cells right here, subject to these constraints. First of all, this column must be less than or equal to the values in this column. Add that with OK. And then we want to add these two values must be less than or equal to these two values. So actually, let me get this right. B20, oops, solver, add. B20 and C20 must be less than or equal to these demand figures. B22 and C22. Click on OK. Okay, make sure that this checkbox is checked and that you've selected the simplex linear programming method from these three here, and then click on Solve. And you can see what it did was it says that you should ship 0 product from plant 1 to South Korea, but ship 44 million pounds to France, and that will be put plant 1 right at its capacity. Then from plant 2 you'll ship 24 pounds from South Korea to South Korea from plant 2, and 4 million pounds from plant 2 to France. And then that means that your total profit in millions will be 2.764. Okay, and that gives you what your optimal solution is. So what I would like you to do is I would like you to analyze this. Why did it decide not to ship anything from plant 1 to South Korea? Why did it ship everything from plant 1 to France, for example? See if you can reason through that. It's not going to be immediately obvious, but you should be able to come up with some preliminary conclusions, because this problem is a little more complicated than some of the other ones that we've done. But that's how you do a maximization transportation problem.